work and what is energy. Energy is just the capacity to do work. By the way, this is chapter 3 in your book, so I'm following along in the book. Energy is the capacity to do work. Oh, and let's not forget that we'll have a quiz. You know what, guys? Let's go ahead and do the quiz on Tuesday. Is that going to freak you out too much? Do it on Tuesday? All right, we'll do it on Tuesday. I'll send an email out about that quiz. That'll be on chapter 3. So go ahead and read that chapter. Remember, the quizzes I take straight from the chapter. I try not to take just minutiae from the chapter, but big ideas from the chapter. So look to that end for the big ideas in the chapter. All right, so energy is the capacity to do work. And this physics definition of work involves force and displacement. So work is done when a force causes a displacement. And just to remind you, right, a force is a push or a pull. And displacement is a fancy word for just distance, right? So this is a change in position. It's a little bit different from distance because we'll see that displacement will have a direction attached to it. That you can either go in a positive direction or you can go in a negative direction when you're talking about displacement. And you'll need to include that whenever we're determining what is the work being done by a force. If an object has forces acting on it but no motion, I'm going to leave sort of a parenthetical here. I'll go and put the parenthetical in. But no motion in the direction of the force. Then no work is done. All right, so a couple of things. If I stand here, there are all sorts of forces acting upon me, correct? Right. But they're not doing any work because I'm not moving around. Okay? Now if I jump up like that, then there is work being done. I'm doing work because I'm applying a force upwards with my legs. That's pushing me up in the upwards direction. And so the force and the displacement are in the same direction. And so that force is doing work. Now, if instead, if I take an object, here I'm applying a force, right? I'm applying a force. What's the direction of the force? It's up, right? So the force is up here, right? But what if I move this object from side to side? What kind of work is that upward force doing? Is it doing work or no? No, it's not doing work because the force is up, but the displacement is side to side. And so those aren't in the same direction. In fact, they're perpendicular to one another, and so that does no work. I'll write this out in just a second. It's sort of a mathematical type. All right, so work requires a force and a displacement in the same direction. So wait, I was in the gym the other day, and there was a guy, I think it's Justin Homer. Plays baseball? Is that Justin Homer play baseball? Or is it Justin Holt? Y'all know him? He was jumping. You know, they had those things in the weight room, those like platforms that people step up on. He put two of them on top of one another, and it came up to here. He could jump onto that. Well, I'm not usually that impressed with people in the weight room, but this was impressive. Can y'all do that? He was jumping up here, not hanging on or anything. He just what that? He could jump on top of your head. Yes. Very impressed. All right. All right. So if an object has forces acting on it. Okay, so mathematically then, we would say that work is equal to the product of the force and the displacement when these are parallel to one another. Parallel or anti-parallel to one another. That means that the force and the displacement are in the same direction, but what does anti-parallel mean? In an opposite direction. I'm going to draw a picture here. I'll show you what this means. However, when the force is 90 degrees or perpendicular to that displacement, then there is no work done. This comes out, don't write this down if this confuses you, but this comes about, the actual expression for work is work equals FD cosine of theta. Remember the cosine? You probably had it in high school. It's a trigonometric function, and it describes the cosine of the angle theta. If theta is equal to 0, then cosine of 0 is 1. If theta is equal to 180, then cosine of 180 is negative 1. Okay, but if cosine of 90, if theta is 90, what is cosine of 90? It's equal to 0. So it comes about from that. Let me draw a picture. I think that'll probably help you understand better. All right, so if I have an object that has a force applied to it in this direction, and it's moving, let's say all these objects are moving with a displacement in this direction, then this object is going to have a positive work, right? Because the force and the displacement are in the same direction. However, if I have an object that has a force acting in this direction, and it's moving to the right, so I have a force to the left, but the object is actually moving to the right, then what is the sign of the work in this case? Do I have positive work, negative work, or 0 work? Let's do this as a clicker question. Is this positive work? B, negative work? Or C, work equal to 0? Oh, give me just a second, I have to pull it up.
One way and displacements the other way?
That's right. And you can have a situation like that, right? Like imagine that you have, you have a football player, right? And they put on those harnesses and they're dragging the sled or whatever, right? You have the force due to friction of the sled, which is pulling backwards on the football player, but they're pushing forward. So you have a displacement in one direction, but then you have a force that's in the opposite direction. You follow what I mean by that? Right? Because you have displacement in one direction, but a force in the opposite direction. Now there are other forces at play, of course, right, that is causing it to move forward, but we're isolating a single force. Okay, so in this situation, with the force to the left, the displacement to the right, positive work, negative work, or 0 work. I'm going to stop at 42. 42. All right, very good. B is the right answer. When the force and the displacement are opposing one another, I have negative work. Let's imagine now that I have an object. It has a displacement to the right still, and I have some force that's acting in that direction. Which of these is true? Is it A, positive work, B, negative work, or C, zero work in that case? All right, I'm going to stop at 23, 20, or 25 rather, 25. Okay, very good. C is right. It has zero work, right? Whenever the force and the displacement are perpendicular to one another, then it's zero work. That comes about because of that cosine term. The cosine of 90 degrees here is zero. Or if that confuses you, just know that when the force is perpendicular to the displacement, then that means that it's not doing any work. All right? Let's consider this situation. Let's say that I have an object, it's still moving to the right, and I have a force that is at an angle in that direction. What is the work that's being done there? Is it doing positive work, negative work, or zero work? Now in this case, it's neither parallel nor perpendicular. Okay, doing a good job. Just a few more seconds, I'll stop at 40 seconds. If you're not sure, ask your neighbor. Very good. A is the right answer. Good thinking there. Now, in this case, we've talked about vectors, how we can divide a force up into its separate vectors. So I can think about this force as having two components. It has a component that is up, like this. This one does zero work, by the way. And then it has another component that is in this direction, and this one does positive work. Right? So this component of the force is in this direction, the same as the displacement, and it does positive work. All right, so just to summarize those rules, when the force and displacement are in the same direction, that gives us positive work. When force and displacement are in opposite directions, that gives us negative work. And when force and displacement are perpendicular, that gives us work equal to zero. So it gives us zero work. All right, one more thing. We talk about this idea of positive, negative, and zero work, right? In the past, when we've talked about object or quantities having signs, what does that mean? If something is negative, what does that mean? What does the negative signify? Like say with a force, if I have a negative force, what does that mean to have a negative force?
It's an opposite direction motion.
Right. So it has something to do with, what was the word used?
It's an opposite direction motion.
Right. It has to do with the direction. So if I have something that has a negative value attached to it, then that means that it has something to do with the direction. So we didn't really get much into vectors in the first chapter, but it has a lot to do with vectors. Anytime we have a negative value, that usually means that it has to do with direction. So if I have a negative displacement, that means I'm moving in the negative direction, which we take to be what? Left or right? Left, right. So left, yes. We take negative to be left. Up is down. Up is positive, down is negative. In this case, that's not the case. So in this case, when we have work, a negative work, that doesn't mean that it's in a negative direction. Because work isn't a vector quantity. Work is what we call a scalar quantity. Vector quantities have magnitude and direction. That means they have a value and they have a direction. A force, for example, is a vector. it has a value, say Newton or whatever, a direction, negative, down, negative, left, whatever, or positive, up, positive, right. Time, on the other hand, does it have a direction attached to it? No, it doesn't. It's a scalar quantity. Likewise, mass is a scalar quantity, charge is a scalar quantity, and work falls under the scalar quantity. So work is a scalar quantity. So then what does it mean when we have a negative work? Go back to our definition of work. Or rather, energy, which is the capacity to do work. So what do you think it means then if something does negative work? What happens to the energy? Now, if something does positive work, like for example, I'm going to do positive work on this chair. I'm going to pull out in this direction, right? Pulling up, by the way, so the friction is less, right? Y'all done this at the grocery store? Who's tried it? Where you pull your, did you try this, Emily? No, okay. So anyway, I'm doing positive work on this bit. Would you agree? If I'm pulling it in this direction and the displacement is in this direction, what am I doing to its energy? At first it was at rest, and then it's moving. So what have I done to its energy? I've increased the energy, right? But if on the other hand, if somebody was pulling it in that direction and I was holding it back, what would I be doing to its energy? Follow what I mean? Like if it's traveling along in this direction, but I'm pulling it back in this direction to slow it down, what do I do to its energy in that case? I'm decreasing the energy. So in that case, I'm doing negative work. So what it means to do negative work is to decrease the energy. So positive work doesn't have anything to do with direction. It just means I'm increasing the energy. If I do negative work, I'm decreasing the energy. Let me write that down. All right, to do positive work means you increase the energy. To do negative work means you decrease the energy. And that's what the positive and negative means there. That you're either increasing the energy or you're decreasing the energy. All right. Let's do a few questions. All right, so is it possible to do work on an object that remains at rest? You have an object that's sitting there, but you have forces acting on it in whatever way. Is it possible then to do work on that object if it remains at rest? Okay, remember that our work is equal to the force times the displacement. So you need a force that's non-zero and a displacement that's non-zero in order to do work. All right, good. Just a few more seconds. I'm going to stop at one minute. Very good. B is the right answer. Because if I'm remaining at rest, that means my displacement is zero. That means I'm doing no work. A box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Doing well. Most of you have the right answer. Feel free to ask your neighbor what they put, okay? All right, I'm going to stop at 45. 45. And B is the right answer. That friction almost always does negative work. because friction almost always acts to slow down an object. Let me show you one example where it doesn't though. Let's say that I have a truck. That's a pretty good truck, right? You like that truck? Now let's say I have a truck and I have a box sitting on the back of it. Now this truck is moving in this direction, so it has a displacement in that direction. What is the direction of the frictional force? There's a force between the surface of the truck and the surface of the box. What is the direction of that frictional force? Remember, the frictional force is always going to oppose the direction of motion. So is the frictional force back or is it forward? You'd think so, wouldn't you? But listen, the box, because of its inertia, it wants to move backwards, right? It wants to stay in place, so it wants to move backwards. So this box, if there was no friction, would move backwards. So then, what is the direction of the frictional force? If the box wants to move backwards, the friction is this direction. So in this case, we have a frictional force that is in that direction. It's a static frictional force. The displacement is also in that direction. So in that case, the friction would actually do positive work. It's acting to speed up the object. All right, in a baseball game, catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Has the catcher done positive work? Has the catcher done negative work? Or has the catcher done zero work? You can think about the force and the displacement. What are the directions of those? Or you can think about what the catcher has done to the energy of the ball. Okay, we're not doing real great on this. What is happening to the energy of the ball? The ball is traveling along at 90 miles an hour, and then what happens to it? It stops. So its energy goes from, a lot to what? Zero. Right? It stops. It has no energy. It's not in motion anymore. So am I giving energy to the ball, or is the catcher taking away energy from the ball? Is he giving or taking away? He's taking away. He's saying, I'm going to take all that energy, and it goes into his mitt, it goes to his hand, and it makes sound, and it goes into his muscles, but he's taking away energy from that ball. Right, so what does that mean as regards to the work? Has he done positive or negative work? I'm going to stop at 135. All right, good. Okay, excellent, good. The answer is negative work. He's taken away energy, so it's negative work. You can think about it too. If I have this ball and it's traveling along in this direction, the mitt, this is the mitt, sort of looks like a mitt, he has to exert a force in this direction, all right, but the displacement is in that direction. So they're in opposite directions, so that means negative work as well. A ball is tied to a string, it's being whirled about in a circle. What can you say about the work done by tension? You might not know this right off. So I have this ball. It goes around in a circle. What is the direction of the tension? Like it's tied to a string. In this, at this instance, what is the direction of the tension? It's in this direction, right? It's pointing, in this case, to the left. So the force is in that direction. And I want to know what work is being done by that tension, by that force due to tension. Does it do no work? Does it do negative work? Or does it do positive work? The question here you want to ask yourself is, what is the displacement? What is the direction of the displacement in this case? pretty well. Ask your neighbor what they put. A lot of you have the right answer, but a few of you don't. So ask around. Ask your neighbor what they put. Or just volunteer your answer to somebody. All right. All right. What is the direction of the displacement? What do you think? You might not know this right off. We haven't talked about this. What is the direction of the displacement? Perpendicular to what? Force. Right. So in this case, if it's going around in this direction, my displacement is perpendicular to the force. So in this case, my displacement is in this direction. All right. Change your answer if you like. I'm going to give you a few more seconds. I'll stop at 223. 223. Good. All right, so in this case, the tension, because it's perpendicular to the displacement, does no work at all. So in fact, that tension doesn't do anything to affect the velocity or the speed of the ball. There are other forces that do that. All right, we'll come back to this. We're going to do kinetic energy next. All right. So when we talk about energy, we have lots of different kinds of energy. One of those is kinetic energy. This is the energy of motion. All right. The kinetic energy, I think your book just uses K. Sometimes people use KE. Let me see what they use. Yeah, they just use K. All right, so the kinetic energy is just 1/2 mv squared. All right, where this is the mass, and this is the speed. In this case, it doesn't matter about the direction of this quantity, because if it's negative, right, we can have a negative velocity, something traveling in the negative direction. But if this quantity is negative, it doesn't matter because it goes away, right? The square of a negative number is a positive number. So I'm just looking for how fast it's going. I'm not really worried about the direction at all. If you do work on an object, the energy changes. This is called the work energy theorem. You don't need to know what it's called, but it is called the work energy theorem. And it just says that if I do work on an object, then I change the energy. And with certain forces, you're going to change the energy by the same amount. So if I do work on an object, then I'll change the energy. This is kind of an interesting thing. There's a cool history behind this expression for the kinetic energy, this 1/2 mv squared. Back in like the 1700s, people didn't really like dealing in squared numbers because they thought that they were satanic. They thought that they were inherently evil in some way, which is kind of crazy. I mean, when we think about it now, it's like, well, that's just superstitious. But it was crazy then too, because they used a lot of squared numbers, right? How did people use squared numbers back in the 1700s? A lot, actually. What did people do in the 1700s? Well, they would build things, yeah, but I mean, the main thing that they did was to farm, right? See a little house on a prairie, like they spent a lot of time farming because they just have to make their own food. We don't have to do that now, of course. So how are squared numbers relevant when you're farming? If you're a farmer. Right. You only need to know the amount of land that you have, so you can determine, you know, how many seeds you need, or how much crop you're going to get from a particular plot of land. So there are a lot of calculations that you have to do that involve square numbers. But back then, for whatever reason, they thought that these square numbers were evil. And so scientists at the time, science was sort of a new thing where you would do these experiments and figure out relationships between physical quantities. They thought there's no way that the amount of energy that an object has can be proportional to the velocity squared. And there was this a woman scientist, which was strange in its own right because women didn't really do science at the time. But her name was Emily de Chapdelaine, and she came up with this experiment. She was French. She came up with this experiment to determine what is the relationship between the kinetic energy and the velocity. And it was kind of interesting. You don't need to write this down. This is just sort of for your own interest. But it was interesting. Just the way she did it was pretty simple. She took some clay and she dropped a ball. She took a ball and she dropped it into the clay so that when it struck the clay, it had a velocity v. And then the ball made an indentation in the clay, and she measured this, and it had a depth h. And then she dropped the ball from a higher height so that when it fell to the clay, it would have twice the velocity. And how far do you think it dropped down into the clay? Did it go down twice the height or some other value? If it has twice the velocity, how much more energy does it have? No, not twice. Because remember, yeah, we have this quadratic relationship. So if I double my velocity, this is important, by the way, for the test, but if I double the velocity, that means I quadruple my kinetic energy. And so what she found with this very simple experiment was that instead of going down twice the height or twice the depth of the first ball, that the second ball actually went down a lot more because it had 4 times the energy instead of just twice the energy. So she found that it went down to 4 times the height. It's a little bit more complicated than that, but that was basically the gist of it. And that really sort of blew in the face of what scientists had been saying up until that point. All right. Okay, so let's imagine that you push a car with constant speed. What is the work done? Is the work done A, positive work, B, negative work, or is it C, zero work? What is the, actually I'm looking for the total work done. What is the total work done on this car? Is it a positive work, a negative work, or is it zero work? If I do work on an object, what am I going to do? By the work energy theorem. If I do work on an object, what do I do for this energy? Increase. I increase the energy, right? The work done on an object will increase the energy, or decrease it. It'll change the energy. All right, but positive work would cause the energy to increase. All right, now in this case, I'm pushing a car, but I'm pushing it at a constant speed. So what then is the total amount of work that's being done on this car? Very good. You're changing your mind. You're doing a good job. So ask your neighbor what they put. Most of you had the wrong answer initially. All right, I'm going to stop at 1:30. 1:30. Oh, very nice. Yeah, so it has zero work. Hey, my daughter told me this one this morning. You want to hear it? What is a frog's favorite drink? You can say, I don't know. Coca-Cola. That's a 6-year-old joke. I don't know where she got that. All right. So you push a car with constant speed. Now you're doing positive work, all right? So then why do we say then that it has zero work being done on this? Is something else doing negative work on the car? It must, right now. So it's friction. So friction is doing negative work, you're doing positive work, and the net effect then is that you have zero work at all. So here, zero work is being done on the car because friction does negative work. All right, so if I imagine my car here, right, you're pushing on it in this direction with a certain force, but then I have a frictional force that's pushing in that direction. And they both do equal and opposite, or equal works, but one is positive and one is negative. All right, tell me which of these are the units of work? Oh. Is the unit of work A, Newton meters, B, meters divided by newtons, C, newtons over meters, or D, meters newtons over seconds? Which of these are the units of work? Newtons times meters, meters over newtons, newtons over meters, or meters times newtons over seconds? Remember, anytime you ask for the units, you just want to look at the expression that describes what that is. In this case, either our work is equal to our change in energy, or our work is equal to our force times displacement. And then you can put in the units that you know for those variables and find the units for the work. All right, doing pretty well. I'm going to stop at 115. 115. Okay, good. So remember, work is force times displacement. All right. Forces are in newtons, displacement is in meters, so that means that the units are Newton meters. But look, we can also say, if I break this into its basic SI units, remember force here, this is mass times acceleration. So I can say then that the units of work are also, if I have 1 Newton meter, are also the same as the mass, which is the kilogram, the meters per second squared, that's my acceleration, times another meters, or kilogram meters squared per second squared. These are just the basic SI units, and I just got this. I said that work is force times displacement, that's newtons times meters. Force is in newtons, B is in meters. Force is further mass times acceleration, Newton's second law, right? That mass is kilograms, acceleration is meters per second squared, and then I throw in another distance, so I get meters squared per second squared. Now look, we can just look at the units here. If you remember, the kinetic energy is equal to 1/2 mv squared. So the units of this then are kilograms, v is meters per second, and it's squared. So notice here that these two units are the same. And so the units for work actually are the same as the units for energy, or kinetic energy in particular, or we'll look at some other energies, they're all the same. So units for work are the same as energy. And so 1 Newton meter is equivalent to 1 kilogram meter squared per second squared. And this is equivalent to our unit for our energy, which is called the joule. One joule, this is abbreviated with a capital J. And so that's the SI unit for energy, is the joule, and I'll be using that. But it's very similar to the units for work. It's the same as the units for work. Their definitions are slightly different. All right, a work is a force times a displacement, and an energy is the energy of motion, or we'll see some other types of energies as well. Now, typically, we use what unit for energy? Like when you're just people running around. What kind of units do we use for energy? We use calories, so we use calories. We use those to describe temperatures, thermal energy. Often when we're talking about how hot a substance is, we'll use calories. And then of course we also use that to describe the amount of energy in food items and the energy that we burn as humans. So, but calories are the same as joules. There's a conversion factor between them. We'll see that a little bit later when we get into metabolism and the energy of food. All right. Now there's another type of energy called potential energy. And potential energy is stored energy. We're going to call this U. That's what your book uses. Sometimes in other books you might see a PE for potential energy, but often U is a very, very common variable. The potential energy is stored energy. You can store energy in a lot of ways. We can have elastic potential energy. Right, that's like a elastic potential energy. If I have this rubber band and I stretch it, I've stored energy. I'm not going to speak. Right, I store energy, and then when I release it, it releases that energy. The potential energy then becomes kinetic energy. So you can have elastic. You can also have gravitational potential energy, which we'll deal with. Gravitational potential energy is if you hold something in the Earth's gravitational field, it has the potential for motion, so it has potential energy. How does this have potential for motion? Like the rubber band, if I release it, it would fly off to the side. What about this? Right, if I drop it, then the gravitational force acts upon it, and it has that potential for motion. I can also have electrical potential energy. Our electric potential energy. We'll get into this in a bunch of chapters, not till the end. So we can have different types of potential energy: elastic, gravitational, or electric. There are a few other types, but these are the only ones we'll deal with in this course. Oh, you can also, I'm sorry, no, we'll have another one, which is chemical. So when we're talking about food items, usually that means that the energy stored within them is chemical, and then one more, which we'll see in this chapter, which is thermal. All right, chemical describes the energy that's held between bonds, the molecular bonds in the food or whatever that chemical is. And then thermal energy describes the energy that's due to the molecules just vibrating back and forth. So an object that has a lot of thermal energy or has a very high temperature, the molecules will bounce back and forth a lot. And then if it's really cold, they don't move as much. All right. We'll see each of those types in this chapter, except for the electric potential energy, which we won't get to till later. Let's imagine that if I move an object to a height h, which of these is the work that's being done on that object? A certain amount of work was required to move that object. Which of these is it? Is it mg divided by h, F divided by h, mg times h, or is it m divided by g times h? If I move an object to a height h, what work is required? All right, that means I take this object and I move it from the ground up to a height h. How much work is required? Been really well so far. Feel free to ask your neighbor what they put. All right, I'm going to stop at 55. I think that's everybody. 55. Very good. C is the right answer. Remember, our work is just force times displacement. If I'm moving an object from this point, h equals 0, to this point, h, I apply a force over a certain distance. My work is that force times that distance, and that force required to move this object is equal to its weight. So that's mg times h. So if remember the work energy theorem, work is equal to the change in energy. This book on the floor has how much energy? When it's on the floor, how much energy does it have? How much potential for motion does it have? It has 0 work, or 0 energy. But if I move it up to a height h, what is the energy that it has? It has this energy. It has this mgh. And so I can calculate then how much energy it has in joules, just as m times g times h. So for example, let's say that I moved it to a height of 2 meters. Let's say that it had a mass of 1 kilogram. Then the amount of potential energy that it has, which is mgh, this will be on your equation sheet, by the way, but it's equal to m times g times h. That's 1 kilogram times 10 meters per second squared. That's our acceleration due to gravity. That's just the weight of the object, times h, which is 2 meters. That means that it's going to have 20 joules of potential energy. This 1 kilogram object that I hold 2 meters above the floor has 20 joules of energy. Now, when you drop this, if it has 20 joules of energy up here, what happens when I drop it to the energy? Or what happens first to the potential energy? When I drop it down to the ground, what happens to the potential energy? It goes to 0, right? So we've already seen that. The potential energy here is 20 joules. Here it's going to be 10 joules. And then when it's down on the ground, it's going to be 0 joules. But something else is going to happen as it's going down. What happens to the book as it moves down towards the ground? What happens? Okay, yes, that's the answer, but what more basic than that? What happens to the speed of the book? Increases. Right, so the speed of the book increases. As I drop it, the speed increases. It accelerates towards the ground at that rate of 10 meters per second squared. But the kinetic energy is also going to increase. So we'll find then that when I release this book, or whatever it is, if up here it has a potential energy equal to 20 joules, as it goes down, the kinetic energy will increase while the potential energy is decreasing. Right, we'll see this. This is called the conservation of energy. It means that anytime you lose energy, you're going to gain it somewhere else. We'll deal with that soon. I want to watch a little video first, and we'll deal with this. Let's see. All right. We will also talk about later how we'll get into elastic potential energy soon. But our muscles also contain a lot of elastic potential energy. That's what allows us to do certain things like Justin and Isn't that amazing? If y'all know him, baseball player holds or home run again. Nobody knows him. He's a baseball player. Ask him if you ever meet him. All right, I want to be just like them. Let's see. Okay. So let's look at mechanical energy. Mechanical energy is just a way of saying that it's the sum of our potential and our kinetic energy. He talked about in that video actually how, you know, the energy changes back and forth, and at certain points she has either potential energy or just kinetic energy, and also at some point she has both potential and kinetic energy. So mechanical energy is just the sum of U and K. That's the potential and the kinetic energy. So if we just call it E for mechanical energy, that's just equal to our gravitational potential energy plus our kinetic energy. And then this idea of the conservation of mechanical energy. It just says that energy transforms from U potential to kinetic energy and from kinetic potential, but the total is always constant. So E then is constant. If I have a certain amount of energy in a closed system means that there's no energy coming in or going out, then the sum of these energies is always going to be the same. So this is only true for closed systems. All right, only true for closed systems where there's no energy coming in or going out. All right, let's consider a problem. Let's say that we have a roller coaster or say a bead on a wire. Can I go down? All right, so let's say that we have a system that's set up like this. All right, let's say that I have an object, a roller coaster here, and it has a certain amount of energy. Let's say it's at a height of h. Right. Initially, we'll just say that it has a velocity equal to 0 here. Let's consider that I have several locations along this. I'll call this location A, location B, location C, and location D. At which of these locations does it have the most potential energy? Where does it have the most potential energy? A, B, C, or D? So this roller coaster is going to take off. It's going to come down here, come up and over here, and then up here it'll come and stop at some point. Where is it going to have the most potential energy? At point A, B, C, or D? We'll wrap up soon. I'm going to hand back your exam, so let's just do a couple of questions here. At point A, B, C, or D, where is it going to have the most potential energy? Feel free to ask your neighbor. Most of you have the right answer. A few of you are a little off. So. All right, I'm going to stop at 108. 108. Okay, very good. A is the right answer. Where it's at the highest point has the most potential energy. Where does it have the most kinetic energy? Remember, kinetic energy is that energy of motion. So where does it have the most kinetic energy? At point A, B, C, or D? Stop at 35, 35. Okay, we're sort of split here, but it has the most kinetic energy at point B, because whatever potential energy it had up here, right, it only has potential energy up here. Up here, the kinetic energy is equal to 0. Here, the potential energy is at its maximum. Down here at the bottom, it now has no potential energy. That's equal to 0. And so the kinetic energy is at its maximum. And whatever potential energy it had up here, U, it's going to have a kinetic energy down here. All right, so it's going to have the most kinetic energy down here. Remember, the sum of these two have to always be the same. All right. Where is it going to be going fastest? At point C or point D? So, oh wait, no, I'm sorry. Nix that. Except for point A, where is it going the slowest? All right, I know at point A it's going with a 0 speed. So, except for point A, where is it going the slowest? At B, C, or D? Where is this car going the slowest? B, C, or D? Where it's going the slowest, also by the way, will be the same as where it has the least kinetic energy. So wherever it has the least kinetic energy is where it's going to be going the slowest. Okay, very good. A few more seconds, I'll stop at 40. All right, good. C is the right answer. It has both potential and kinetic energy. Both of these are greater than 0 here, but it has more potential energy here than it does here. So then it also has less kinetic energy here than it has here. Let me ask you one more question. Let's say instead of having V equals 0 up here, let's say that V is greater than 0. So when it comes off the top of the roller coaster, it has a speed that is more than 0. So when it comes over here, where is it going to go? Is it going to go to some point above that line, on that line, or below that line? That roller coaster cart is eventually going to stop, right, as it goes up this hill. Is it going to stop at a point above its initial height, at its initial height, or below its initial height? At A, B, or C? A being a point above the height, B being at the same height as where it started, or C being some height below? Okay, remember, I have a different beginning condition here. Before we were saying that the velocity was 0. Well, let's say now that the velocity is not 0. So up here it has both kinetic and potential energy, right? Over here when it stops, what is its kinetic energy going to be? It's going to be 0, right? Because it stops, so it's 0. So that means that all of this energy that was over here, the kinetic and the potential energy, where the kinetic's not 0 anymore, is going to go into potential energy over there. So how is that going to affect where that object stops? Is it going to stop at point A, point B, or point C? I'm going to stop at 118. 118. All right, so A is the right answer. It's going to go, if our kinetic energy is greater than 0 over here, that means it's going to come up to some point above where I started, because the total amount of energy is always going to be the same. So over here I have a certain amount of kinetic and potential energy, right? But over here I have no kinetic energy, so that gives me extra potential energy over here. All right? You'll see some problems like that on the test. We're not going to do any calculations from the conservation of energy, but you'll have scenarios like this where I ask you, what happens to kinetic energy here? What happens to the potential energy here? Okay? All right. I'll go ahead and hand back your test. I think is that a good stopping point? Yeah, that's a good stopping point for now. And I'll go ahead and hand back your test. Now let me show you something, because I have placed the test online. So if you go to this website, which is linked on Moodle, and go to the old exams, you can find exam 1 here. Now, as you know, on your exam, the questions aren't marked right or wrong, so you can go down and they're all right here. Okay? The true-false was not kind to y'all. You did not do so well on the true-false. You should do well on the true-false, but they were a little bit, I don't want to say tricky, right? But you had to really think about them. Because I never want to trick you. That's not my goal in life. Yeah, Jason?
Is the final,
No, final's not cumulative, so I guess that's good. Is that good? Yeah, the final's not cumulative. The final is just going to be an exam, but we'll have it on at the time of the final, right? When it's scheduled, it's in the syllabus that way, but not cumulative. All right. Y'all excited about a quiz on Tuesday? It's good. Go ahead and read that chapter. It's good. You need a good kick in the butt to read that chapter. Soon. All right. So it'll help you understand this more when we get to it. So we'll do that quiz on Tuesday, and I'll send y'all an email about that reminding you. All right. Let's see. What's up here? So I'm going to call your name for the forms. You can come get that, and then I'll call your name for the other part, and then you can go. So Brianna, Juana, Kylie, and Mel, you're all going to stand up here. So. Jason. Because there weren't a lot of A's. Alright, so if you made a B, you can do really proud. B was good on this exam. But the average overall was pretty good. I mean, we were pushing a B average on this exam, so that's pretty good. But it's just the way they fell. There weren't a whole lot of A's. Alright, so Brianna, y'all just come on up and go. Actually, look, guys, I'm just going to put them up here. These don't have your scores on. So when I call your name, you can come get it. Jason, Noel, Lucio, Corey, Olivia, Josh, Brent, Michael,